In this lecture, we will discuss about the AC circuits. This lecture covers the introduction about the AC circuits and the generation of AC and how do we represent the AC signals. To start with the introduction of AC circuits are basically those electrical circuits which are powered by the AC sources like alternating voltage or current. So such circuits we call as the AC circuits. Now, what is an alternating voltage? An alternating voltage is, any voltage which varies both in magnitude and polarity with respect to the time. Similarly, we can say that an alternating current is any current that varies in both magnitude and direction. So, you know, an alternating voltage varies in magnitude and polarity, means the polarity and magnitude both changes with respect to time. However, an alternating current varies in magnitude and direction, means the direction of the current and the magnitude changes or varies with respect to time. AC circuits, as the name implies, basically are the circuits as already mentioned, that those circuits which are powered by the alternating sources. When we say powered by the alternating sources, we mean to say that those circuits which are run or operated through the AC sources, alternating current or alternating voltage. Now let us see what are the advantages of AC circuits or AC systems basically. The first advantage of AC is that it is very economical to generate, transmit, and distribute an AC signal. Now we are actually talking about the electric signal here, right? Then it is very convenient to convert AC to DC, so we can use rectifiers for that. So it is convenient to convert an AC to DC. Control of AC signal can be carried out without much loss of electrical power. It means that we can control the magnitude and phase or the various quantities of AC without affecting the losses, without increasing the losses or with the minimal losses basically. It is convenient to increase, that is step up or step down the level of the AC with the help of transformer. Now, transmission of AC to long distance is very economic and cost effective because it can be carried out with minimum loss of the electrical power. And uh, generally, we can say that the AC systems can be used in more effective and efficient manner as compared to DC. Now, let us see a little bit more comparison between AC and DC. Because your AC is a bidirectional signal, AC, it is a bidirectional, and DC is basically a unidirectional. So when we say unidirectional, we actually mean to say that with respect to time, it remains with the same direction. It does not change its direction or polarity. However, a bidirectional signal may vary with respect to time. Okay, so time axis would be the mean position for such. So now, as far as the comparison is concerned, so the first comparison is um, on the basis of the symbolic representation of the AC voltage source and DC voltage source. An AC voltage source is represented in this way, and DC voltage source, as we have already seen, is represented in this way basically. Um, an AC voltage source has sine wave inside, or a sine wave encircled basically. So this symbol can be used for both AC voltage as well as current source. Now the summarized comparison of AC and DC is given here. As far as the energy transmission capacity is concerned, AC can be transmitted to a long distance, and the losses involved, losses of energy or power involved in the transmission of AC are minimum as compared to the DC. If the same amount of DC is to be transmitted to long distance, to the same distance, so in that we need you know there is a large amount of energy is lost basically. So uh, it is not convenient to transmit this, and also not cost effective because it needs some additional installation of various other components in the system. So an AC, because it is a bidirectional signal, so it has frequency. So globally we have either 50 hertz system or 60 hertz system. However, a DC ideally has zero frequency because DC is generally represented with a constant line, and AC is generally represented as a sinusoidal wave with respect to time. Direction. So periodically, because it is a bidirectional signal, so periodically it reverses its direction and polarity, of course. However, a DC remains constant throughout the time. The magnitude of current varies with time. The magnitude of current in case of DC remains constant with respect to time. All the AC generators are basically the source of AC. Generally, we call them alternators. However, the source of DC are cells, batteries, solar cell, conversion from AC means through rectifiers. Then waveform, the representation of AC is either sinusoidal, trapezoidal, triangular, or square, means any signal which is bidirectional in nature. Let us say a sine wave or a square wave or a triangular wave or any signal which is bidirectional, random signal which is bidirectional. So all such signals are basically the alternating signals or AC signals. However, a DC is represented with a straight line, or it may sometimes be pulsating. For example, in case of the output of a rectifier, the output of rectifier is something like this. Let us consider a full wave rectifier. So it is something like this. So this is we call as pulsating DC. So remember one thing, that DC is basically a unidirectional signal. It has only one direction. Either it would be positive or negative. That is a different thing, but it would have a one direction. However, AC is always a bidirectional signal, right? Now let us come to the representation of the alternating signal. As I have explained here also, that we can represent the AC signal as sinusoidal wave, trapezoidal, triangular, square, like that. So graphically we can represent the alternating signals as sine wave like this, or any complex wave. It is also, because it is a bidirectional signal, its magnitude is changing with respect to time, and it is also reversing its direction around the time axis, right? Similarly, we have a triangular wave which is also varying. The magnitude is varying with respect to time, and you can see about the time axis, which is the mean position, it is reversing its direction. And similarly is the case with square wave, right? So these are the general representation, but the alternating signal that we use in our electrical systems is basically a sine wave. Okay, so because it is a bidirectional signal, alternating signal is a bidirectional signal, and it is changing with respect to time in terms of the magnitude. As you can see, the magnitude at every point of time is changing and varying, and also after, you can see pi radians, it is reversing its direction too. So here also the magnitude is changing with respect to time, right? So because it is a bidirectional signal, so there are certain things that we need to learn, like um, it has a time period. This is what we call as time period. So time period is basically the time taken by one cycle of an an alternating signal to uh, complete, right? Okay, so when the alternating signals one cycle takes is completed basically, so that time taken by that signal is termed as the time period, right? Uh, whereas the frequency basically, f, it is given by 1 by t. Frequency is the number of cycles of an alternating signal passing through a point in 1 second. So this is what we call as frequency, and it is always term measured in hertz basically, right? Then it is a waveform, right? It has period, time period, which we call it is periodic waveform, and it is symmetric also, periodic. It is repeating itself after a certain constant interval. Now let us come to the most important part of this lecture, which is the generation of alternating voltage. How the alternating voltage is generated. Basically, the generation of any alternating signal is based on the Faraday's law of electromagnetic induction. Now, uh, Faraday says that if you have a conductor, and this conductor is placed in some magnetic field, so this magnetic field is stationary. So it is, now this is a conductor, and when this conductor is rotated with certain angular velocity in a fixed direction with constant angular velocity, so this conductor will have an EMF induced over it, which is given by minus d phi by dt, right? The another thing that is associated with the generation of electricity is that if we have a magnet, basically we have a magnet, and this is, let us say, the axis, and if it is rotating, and then we have certain conductors placed here around its periphery. So if this magnet is rotating and these conductors are stationary, they are static, right? And this field, magnetic field, is rotating, then also these conductors will have certain EMF induced, which is given by this equation, right? So both methods are employed to generate the alternating voltage or electricity, right? So in this we will study uh, about the first case basically. So the alternating voltage is generated in two ways, as I discussed just now, by rotating the coil inside the uniform magnetic field, or by rotating the magnetic field around the stationary coil at a constant speed. So these two representations are shown here in figure A and figure B. So in this you can see you have static, you have magnets, permanent magnets basically. So these permanent magnets are producing uniform magnetic field, which is static, stationary, and within this static magnetic field we have a coil basically which is rotating in a particular direction with a constant angular velocity. So we will have certain EMF induced on this particular conductor. And similarly, we have the second method, the figure B, which represents, you can see this is north and south, as you can see here. So this is a magnet, This is a magnet, and these two are the conductors basically, right? So the magnet is rotating, conductors are stationary. Okay, so this is also one of the way to generate the electricity. Now, whatever is the case, whether it is the first case or second case, the voltage which is generated will be a sinusoidal waveform. Means the nature of the voltage EMF generated through this method, through these principles, will be a of sine nature. Basically, it will have a sinusoidal nature, right? And when we say sinusoidal nature, we actually mean to say that the voltage will vary sinusoidally like this with respect to time. Okay, so the magnitude of the voltage generated depends upon three important factors which are listed here. The first is the number of turns of the coil, and the second is the strength of the magnetic field, and third is the speed of rotation, right? So generally, the first method, which is this one represented by figure A, is used in small AC generators. Small AC generators means the AC generators which with low power rating, right? And the second method is used where we have to generate a very high voltage. Now let us see the equation, the derivation through which we will derive the equation of voltage and current. Uh, Let us consider a coil of n turns basically, which is rotating in some anti-clockwise direction with some angular velocity omega radians per second. And the coil is placed in uniform magnetic field, and it is shown in the diagram here. So, as it is already mentioned that the EMF that would you induce in the uh, coil would be of sinusoidal nature. So we will derive that particular equation here, right? So there are two figures here, figure 1 and figure 2. So this is the conductor basically, or you can say the coil, because coil is made up of the conductors itself, so we can call either conductor or coil, right? So this coil is placed along this axis OX basically. Let us say this is OX. So the plane of the coil is basically perpendicular to the magnetic line of force. So this is magnetic field. So this is your north and this is south basically. And we know that the magnetic field or magnetic line of force, they flow from north to south, right? So the plane of this coil is perpendicular to the line of force basically. Now let us assume that this coil tends to rotate in anti-clockwise direction with some angular velocity omega, and it tilts at certain angle which is theta, which is equal to omega t. Theta is equal to omega t, where omega is the angular velocity. This is the angular velocity, and theta, we can say that it is the angular displacement. Now there, this phi max basically, okay. So because when the coil plane, the plane of the coil is perpendicular to the line of force, like here. So this is the plane of the coil, it is perpendicular with the line of force. So at this point of time, it is interacting with the magnetic field to its extent basically, okay, extreme condition. So here we have phi max, phi, where phi is basically the flux. Phi is flux. So maximum interaction of flux with um, conductor is happening in this particular position. And let us say when it tilts to certain angle theta, so this phi max will have two components. The one is phi max sine omega t, which is coinciding with the plane of the coil, and it is parallel with the plane of the coil, you can see, right? And the second component is phi max cos omega t. So this particular is perpendicular to the plane of the coil. So this is the plane of the coil, and it is perpendicular with the plane of the coil. So so these two components will be responsible for either generation or induction of the EMF on the coil, or no induction of the EMF on the coil, right? So this phi max, uh, let us remove these parts from here. Now, okay, so these two components are there, right? So out of these two components, the phi max sine omega t, because it is parallel to the plane of the coil, and hence this particular component is not having any EMF induced over the coil. Means this component is not responsible for the induction of EMF on the coil, right? Similarly, the component phi max cos omega t, which is actually perpendicular to the plane of coil, you can see here once again. So this factor is perpendicular to the plane of coil, 90-degree. So the EMF that would induce on the conductors or on the coil is because of this particular component phi max cos omega t. So it is actually the responsible component for the induction of EMF on the coil. Now, according to the Faraday's law of electromagnetic induction, as I have already mentioned before, that the EMF that induces in the coil is basically equal to the rate of change of the flux linkage of the coil. Means the amount of flux linking with the coil, right? So it is basically given by phi. So you can say that the velocity, the voltage induces on the coil is given by minus d phi by dt, or you can also write it in terms of EMF. So it is equal to minus d phi by dt. So where phi is the flux linkage, this one. So let us derive this equation. Now, according to Faraday's law of electromagnetic induction, we have this equation here where phi t is the flux linkage, right? Now, the flux linkage phi t is basically equal to the number of turns. Means you can say this is the total flux basically. All right, this is the total flux here. Now this is equal to the number of turns into the flux linking to each turn. Okay, so every turn, because in this diagram we have shown only one conductor, but we may have n number of turns in a coil. So all those n number of uh, turns of the coil would be interacting with the magnetic field, right? So by using this relation, we can have phi t is equal to n, where n is the number of turns of the coil, right? And the flux linking. So flux linking, we will consider that component of phi max, which is actually responsible for the induction of EMF, and that component is phi max cos omega t. Now, if we substitute this phi t in this equation here, so we will get a new equation which is V is equal to minus d by dt. And then we have this equation here and phi max cos omega t. Now that means we have to derive this particular uh, equation with respect to time. Now here n, because it is constant, and phi max is also constant, so we have taken them out and we are getting the differentiation of cos omega t with respect to t. So on solving this equation we get, because d cos, the derivative of cosine of omega t is omega minus omega sine omega t, that is d cos omega t by dt is it is equal to minus omega sine omega t. So this is what we have put here, right? So now minus minus sign will be cancelled out here. So we have v is equal to n omega phi max sine omega t. Or we can also write it in like this, n omega phi max sine theta, because theta is equal to omega t, right? So now in this equation we can see that the velocity, the voltage induced on the conductors depend upon n, and uh, omega, which is the angular velocity. Phi max means the maximum value of flux linking to the plane of the conductors, and then sine of the angle between the uh, OX axis, the time axis, and the plane of the coil. You can see here in this diagram once again, theta is basically the angle made by the plane of the coil with the time axis OX basically here. This is theta, right? So now on keep on solving this equation, we have come to one observation that if sine theta is equal to 1, because sine theta could be maximum 1 and minimum minus 1, right? As per the trigonometric functions. So this could range between -1 to 1, right? So maximum value could be 1 here. So by putting 1 here, we have got v is equal to n omega phi max. So in this equation, if sine theta is equal to 1, v is equal to n omega phi max. Now this is n is basically a constant value, because the number of turns remains same for any generator, right? Omega is also a constant value, because we have already assumed that the conductor is rotating at a constant uniform velocity, and phi max is also a constant value. So that means the product of these three constant values will be a constant or a static value, which is given by Vm. Because this equation we have got for sine theta is equal to 1. So here the value of V will be maximum. So we are calling it Vm, means maximum value of voltage. And Vm is equal to this equation. This is what I was clearing here. Now, so we can replace this part of equation 2 with this one. So this equation number 2 can be modified as V is equal to Vm sine theta. So from this equation number 4, or you can say from equation number 2, it is clear that the EMF that is induced in the coil is of sinusoidal nature, and the because this small v is termed as the instantaneous value. Okay, instantaneous value of voltage or EMF induced on the conductors. So this instantaneous value varies sinusoidally with respect to time. So we can say, we can conclude here that the coil that is rotating with a constant angular velocity in the uniform magnetic field produces a sinusoidal alternating EMF, right? So this is the conclusion. The purpose of this part was just to make you understand that how this sine wave is generated, because all of our systems which we are using, the electrical appliances, most of them are utilizing or are powered by the AC, because we are receiving AC at our home, right, at certain frequency and at certain voltage, right? So we need to understand why do we get the sine wave, right? And the sine wave is obtained in this way. Okay, so you can assume that this is a large generator which we call as alternator. Any generator which produces alternating signal is an alternator, right? So now let us see how what are the various forms through which we can represent the sinusoidal alternating quantity. As we have got the equation number 4 previous slide, which is V is equal to Vm sine theta, right? So if we replace theta with omega t, we will get a new representation, which is V is equal to Vm sine omega t. And we know that omega, which is basically the angular velocity, sorry, not angular velocity, it is angular frequency. So omega is given by 2 pi f, right? So where f is the frequency measured in hertz. So if we replace omega with 2 pi f in this equation here, so we will get v is equal to vm sine 2 pi f t, where this t is the total duration of the signal, the voltage for which it exists. Okay, so then F is basically 1 upon T. So if we replace F with 1 upon T in equation number 3, we will get a new representation of a sinusoidal alternating voltage, which is V is equal to Vm sine 2 pi by T into T, right? Similarly, we can have the mathematical representation of the alternating current. So in terms of theta, in terms of omega t, in terms of frequency, in terms of time period. So theta is basically the angular displacement, omega is the angular frequency, f is the frequency in hertz, and t is the time period, right? So this is how we can represent the voltage, alternating voltage and alternating current in different mathematical forms. So this is it for today's lecture. Thank you so much.